a real honor to be able to chair this first session of this meeting. It's a real privilege to be here, but it's also a real privilege to introduce our first speaker. First speaker is Professor Christian Wessel from the Institute of Biochemistry and Molecular Biology at the University of Hamburg. Professor Wessel started his life in studying physics at Göttingen. He then moved to a PhD, I think, in crystallography at Berlin, and he went to work at Embel at the outstation before returning to Berlin to his home classroom. And then accepted to Hamburg and moved through the ranks and is now a full professor there in biophysics. He's a prolific scientist. He's published over 400 publications. If I summarize him, I think he's following the footsteps of, I think, Francis Crick, who said, if you want to understand function, study structure. He studied structure of a variety of species, plants, parasites, snake venoms, more recently viruses, as we saw earlier. He's also a creator of new technologies, new techniques. Vivo crystallization, I think, was one of his pioneering contributions. He's also done some work with dynamic light scattering algorithms. So I'm really excited to see his talk. Let's all the floor is yours on past and future and structure-based drug discovery to identify lead compounds. Thank you.
Yeah, dear Chairman, thank you very much for the kind introduction. The title is on display, and the reason I'm here is clear. I'm very honored by the organization committee to invite me here and to have a presentation. My presentation is structured in 3 parts, so I first highlight with a few slides the collaboration I had before and in future, and okay, it's back. And then I have 3 subtopics. And on the next slide, you see I'm from Hamburg, Germany, which is in North Germany. We have a nice city lake here. I come back later to this building. It's our town hall, a harbor, and an Elbphilharmonie we see. And the distance is recent, so we reach Karachi from Hamburg in about 10 hours, says by Google, and I can confirm. We have also the University Hamburg, like Tübingen is since 3 years Excellence University in Hamburg. So we have 15 excellence universities. We have 44,000 students, 600 professors. There are some nice statistics that you can Google. This is the main building of the university. And why I'm here, my colleague, late colleague, Professor Felter, invited me 2004 or 2005, together with Professor Lucensko, to join this type of events here. And I came first. And I remember this conference here, you see the chairman and the person today. A very nice conference on natural compounds. And already soon after we started fruitful collaboration. And 3 months later, they see a delegation from Pakistan, Professor Chaudhary and others from the institute here, close to the town hall. And here's in our headquarters signing a memorandum with our vice president. Here's late Professor Felter, and I'm sorry, Professor Chaudhary, I didn't make the picture, I was not cutting you here. The memorandum was very fruitful, and we started. And as you see from these pictures, already 1 year later, I had 4 students. Until now, I have 2 or 3 fellows and PhD students from Pakistan in my group. Very nice collaborations, and already the 2nd generation. Aisha and others are already assistant professors in Pakistan, and I'm board member of midterm evaluation. So the collaboration enlarged substantially and is very nice. And Professor Chaudhary, I should give regards from Aslam. 2 days ago, we have a meeting point close to our faculty's Pakistan restaurant, you see here, and I'm drinking lassi. So we are discussing projects regularly. So the collaboration is very nice and intensive. Coming back to the second topic, X-ray crystallography, I'm entitled my presentation, Past and Future. Hamburg is a nice harbor city, but it's also the city of photon science. Here's the river Elbe, the harbor, and we have a synchrotron facility, one of the brightest synchrotron forces worldwide. It's Petra 3, it's on the DESY campus, and we have a free electron laser, 3.4 kilometers, producing tremendous intensity and radiation, and also time-resolved experiments are now possible. And crystallography, most of you know, you need a protein, you need to purify You can obtain crystals for most proteins, water-soluble proteins, and is a very useful tool in terms of drug discovery. You produce crystals, you look at the structure, you screen against compounds, inhibitors, and that is a lead for drug discovery. Here, a different type of picture and some other points in between. And as you see from the arrows, it's a one-way road. If you have crystals and you are lucky, and most of the time, you obtain reasonable results. Also indicated by the protein data bank, I guess all of you know most well. So there's a substantial, almost exponential increase in deposition over the years, and X-ray crystallography remained the main working horse of this methodology. However, here's the statistics also late 2021, AlphaFold came up, which is a tremendous source and the software to predict protein structures to high accuracy. I was also surprised, and we are using regularly now. This is an amazing tool. You look at, you can predict structures and you can do some reasonable interpretation. So it's a combination of multiple sequence alignment and looking in data banks and coordinates. So there's two lines, and at the end, you have in most cases some prediction. I have to say at this time, there's an accuracy of about 1 angstrom. So in the accuracy in prediction. And the question, of course, is coming out, what is remaining for protein crystallography? So AlphaFold is doing single chain prediction. And however, it has low confidence to partially disordered protein, like the tau protein in Alzheimer's diseases and others. And it has no dynamics, so only one conformation is predicted. And it can till now not predict protein nucleic acid interactions as well as interactions with lead compounds or potential drugs. So this is remaining one of the main tools, and of course we need drug discovery these days. So the future of crystallography is drug discovery. In particular, time-resolved experiments can be performed at this high-intensive radiation sources I have seen just before. And already Linus Pauling predicted, he obtained the Nobel Prize in 1944, that the key, he predicted the key lock system, which is, you see here, you have an enzyme, for example, a substrate inhibitor, and is fitting or is not fitting. However, but already at this time, he was saying the lock is not rigid. Here you see the penicillin binding protein of bacteria. And this is the main target for drug discovery in, say, infections caused by bacteria, penicillin, for example. And you see there's a tremendous activity in the domain movement. And we are following the penicillin binding proteins, I just mentioned this 1, 2, and 3 these days, also by time-resolved experiments. And if you can follow this and just go back, you may have an option for new drug discovery approaches these days. And just here, the picture from Kendall, the screenshots, the first crystal structure published in 1958, and just by single crystallography, single crystal use. The data storage was at this time on tape. Today, you can do almost everything on your mobile. And this was a working horse, I would say, for 60, 50 years. Later, the cryo methods came on top. So you shock freeze crystals from here in the loop and nitrogen free, and this protects them for radiation damage, and you can transport crystals. This was also amazing, well established. But recently, with these sources I have shown and mentioned before, you can collect X-ray data in less than seconds. This is amazing. So I made my PhD, we were collecting protein diffraction data in weeks' time. Then it came down to days and hours, and now you're in the seconds, up to millisecond range. We have the tape drive method. You bring your crystals together with ligands on a mylar tape. Here's the X-ray beam. And you can mix, for example, enzyme, substrate, enzyme, inhibitor, and you can follow up the evolution of the conformation, complex formation. These are jets, so they bring crystals with a speed of 200 meters per second on crossing the X-ray beam. Very interesting is coming up this ship technology. You can bring up to 8,000 crystals in one ship. and bring for data collection here the jets. All this are at room temperature because one shot, one image for data collection, they call it serial crystallography. The disadvantage is you need many crystals, but today we have the methodology to produce many crystals, means 10 to 6 crystals, for example, and you can tackle the time regime. Just again, the 3-electron laser here, synchrotrons here, intensity, and latest detector technology indicating here you can catch up enzyme reactions in the millisecond range if you trigger appropriately. This is a metal block here on the left side showing just how intensive the beam is. So this metal is melted by a 3-electron laser beam, just to give you some impression what the intensity means. And this was discussion some time ago, 2000 they started. Is it meaningful to construct such super expensive radiation sources if the sample, for example, the protein is not surviving? And there were a number of calculations, and then the pilot experiments came by Henry Chapman and John Spence, and they proved it's working. They called it diffraction before destruction. I just recognized my titles behind. And it's working, and then most synchrotrons worldwide changed the philosophy in the last years. Here you see the pins, they are all radiation sources, and they're using this multi-crystal chip technology today to collect data more efficient and fast. I just would like to highlight the facility you are involved with Sesame, and I understand is upcoming, maybe needs some improvement, but is one of the most useful synchrotron sources maybe in the future. And here you see the 3-electron lasers scattered around the world. Just to show you a scheme for those who have not seen my presentations before, this is the end station of the 3-electron lasers, 3 floor levels below ground level. That's the experimental area. Henry Chapman and others, this is the beam station, so you collect data, and I will show examples soon. And it's very efficient these days. Coming to one subtopic, I just want to pinpoint here, antibiotic resistance is coming up worldwide. We have climate change. I appreciate the comment from Dr. Peshua. Today you have floodings in Pakistan. We had tremendous hot summer, so my country is converting to a desert. And scientists have to look at this carefully and to convince the governments to do something efficient. However, antibiotic resistance is coming up, is known for many years. And in drug discovery, normal drug discovery, starting from a target to the concept via organic chemistry, can take up to 12 years. And before, in the particular push by the COVID pandemic, the drug repurposing approaches were coming up to be very interesting, because you have thousands of drugs for one target or 2 targets, and maybe they're functionally also for other targets. And if you apply drug repurposing, means it's already approved, maybe already in the pharmacy, you can save up to 10 years research and development time. And that was one reason we initiated also drug repurposing to treat antibiotic resistance. I just want to mention you have data banks you easily find in the internet. Drug repurposing hub is one, for example. Of course, you do bioinformatics and look carefully before. Now, on this Go Drug Bank, you can screen carefully before what type of target you have and what is meaningful to approach in terms of drug repurposing. As I'm here at the most well-known Institute for Natural Compounds, I would like to mention the natural compounds. We know already today, please correct me if I'm wrong, about 400, 500,000 compounds. The human beings existing of 100,000 proteins with isoforms. So there's a huge library available which needs to be invented. It is invented here on this campus for many years. We heard about this morning. It was invented 2000 years in part, but now it's coming back to look at this type of natural compounds more carefully. So life and biology is maybe, I'm sorry if I'm saying this, maybe a little bit better than organic chemists which concentrate on one target. There's a huge potential. And the potential is here indicated, but also in drug discovery. And I mentioned already here our collaboration with ICCBS, with the Natural compound data bank here. And there are a bunch of journals. I guess our honorable Professor Zaman is editor of one of these journals here, Natural Product Research. Coming back to antibiotic resistance, so you have numbers published in the internet for North America, China, Japan, Europe. And I was screening the last days. I found an article also in Pakistan, the scientists and medical doctors looking more carefully. This is an article from last year showing the evidence, the emerging evidence to look also at antibiotic resistance. Together with colleagues from the university hospital, we are looking at, now I come to one example, at MRSA, the methicillin-resistant bacteria, Staphylococcus aureus. This is colonizing the human body and can turn to be one of the most unfortunate bacteria. I don't need to go in detail on this, just also remembering this. There were fruitful years of drug discovery, most 50 years ago. In recent years, design and discovery for antibiotica is less pronounced. And in terms of repurposing, I showed just two examples. We are looking at the lactamase. The lactamase is hydrolysing the lactam ring of penicillin or penicillin-like structures, which should target the penicillin binding protein. So this enzyme is releasing this from the burden to be inhibited by such inhibitors. And by repurposing, or just to show this, one of the antibiotica just in use these days. You see here the chemistry. You have suicide inactivators. You have beta-lactam inhibitors with novel mechanism. I'm coming to this. And interesting is the boronate-based compounds, which are used also as anti-cancer compounds, for example, proteasome inhibitors. And one result is we screened the data bank using this technology I've introduced, with 400 compounds, and identified bortezomib, which is already known for many years as anti-cancer drug here, is binding via, I would say, the boron warhead to the active site serine. You see here in blue underlines the electron density at 1.3 angstrom resolution is very interesting. And seeing this, we looked at the successor of bortezomib, which is ixazomib, and we see the same site of kind of binding. And this type of compounds are going now in further experiments. Of course, you need to check the cytotoxicity and other issues before approaching cell experiments and in vivo experiments. And now I'm coming back to time-resolved experiments. This is a tape drive. You spray crystals, you mix with the substrate, liquid jet, and the chip technology, which are very common these years in crystallography. You can catch up time resolution, and here a movie started. So we collected data set at the different time points in the millisecond regime, the active site. In the native form, you see a sulfate here, you have the active serine, and just changed the movie to, sorry. Maybe I go to the summary because I'm not familiar with the laptop. We just changed 2 minutes before from Macintosh to PC. Just showing the summary of the movie. This is the native form. You see a reorientation after 80 milliseconds after adding the inhibitor. And you see here, in this case, is boronic acid. You see the formation of a bond close to the ogamma of the active site serine. And you see here it's almost complete with 60% occupancy. And next movie, we did the same experiment by adding glycerol. This was one experiment we did together with organic chemistry, because we see the ester formation of a ester bond at the active site serine. And all this, what you are seeing here, are time-resolved measurements by crystallography. We do in the millisecond range. You see the formation of a bond. This you would never have seen with conventional approaches. And we were surprised, and of course we proved and checked its results and data. So this may be also one initial experiment to look for new approaches to inhibit lactamases, beta-lactamases of bacteria relevant in infection diseases. So you see the formation of the ester bond here. And again, I'm coming to the summary native. First, adding glycerol and boronic acid, you see this type of bond formation, and the electron density is forming up, and the enzyme is completely inactive. These are just pinpoints on recent experiments we performed, and which are possible with our latest technologies in X-ray crystallography, in particular the pulse synchrotron and free electron radiation sources. I'm coming up with a compact summary of our SARS-CoV-2 investigations. All of you know, I don't need to say this, so we have a vaccine. Vaccination is protecting or helping to some extent. And however, the need for drugs is still emerging. We have only one drug reasonable these days from Pfizer, is Paxlovid, but it's not well received by the community, so there's a strong need to look at further options. And already in 2020, early 2020, we decided on the DAISY campus to create a corona research activity. We were targeting, as many other groups, the main protease of the virus, but in parallel also the papain-like, sorry, there's a typing error, protease, the PL-Pro. The PL-Pro is much more difficult to handle. We learned this. M-Pro is an easy enzyme, PL-Pro is, I would say, nasty in the lab, but we succeeded to obtain crystals from both, for both enzymes. We created this research collaboration in the Hamburg metropolitan area, and I was in contact with my good colleague, Professor Shartari. So we also obtained compounds from the metro database from Karachi to start screening experiments. And screening means we were screening, we were crystallizing, co-crystallizing the main protease and later the PL-Pro. You see Hina Amdalib in my group. She's now at Bhutan University. Against compounds blotted in plates before. So we crystallized about 6,000 different conditions. Harvesting, freezing, data collection, all these steps are today fully automatic. So this is again the robot I can really recommend. It's an OREX system. It's very handy. It takes some time, but this is for this type of high throughput screening most ideal. And then we bring crystals frozen to the beamline. Here's a robot and he's taking care. And maybe I'm not sure how many minutes I'm. Okay. This is also a movie on the Mac is starting here. Anyway, the message is here. You can collect data from any place of the world. So we had collaborators at this time in Moscow, in the US, in many places. And they were collecting data from home office, we say in Germany, but can you also in your office, and do the data evaluation. And we find a bunch of very interesting hits already in the beginning, in the middle of 2020 in the active site. This is the main protease, this is the dimer, and here the electron density, and here active site. So you see many compounds. Actually, we found 46 compounds bound to the main protease. Of course, at this time, you have to complement with biochemistry. So we did binding assays, we did cell assays, we did check the cytotoxicity, and we did, we approached also in vivo tests. So we, with Kalpet team, we did in the BSL-3 laboratory with mice and hamster investigations of corona infected. And this is a summary of the compounds we identified, and this is the main hit out of this. And we could publish this in Science. You see there are lots of authors on this because it was a common initiative. So we started from zero in this type of virus research. That's the reason why we have so many. And here are two co-workers from Pakistan co-authors on this publication. I'm just summarizing up on the PL-Pro, and we did the same approach. In this case, we used the Karachi data bank we received on compounds. And interesting is that PL-Pro is not only an enzyme just hydrolyzing the unstructured chain of the virus and supporting the replication of the virus. It's a complicated story. Don't look in detail. I learned this also. The PA-Pro is also interfering with the ESG15, and protein which is in the immune system, very important. And it means, in summary, PA-Pro is reducing, interfering with the immune system of the human. And if you can inhibit this activity in parallel, this is would be amazing. So this is showing the institute. We are now on the campus here. We received the 2,500 compounds. We did the same. We were blotting the compounds in crystallization plates. And we started with 500 compounds, later on harvesting and data collection. Here's the PA-Pro, here's the active site, and here's the region where it's binding ESG15. And here's electron density on the right side for 3 compounds interfering. This comes up to be very interesting in this region here, not allowing any more ESG15 binding. It means the de-ubiquitination of this type of protein. And in parallel with seeing this, we were very excited. We started, of course, cytotoxicity. We did in-cell tests and in vivo tests in line. This just the compounds sitting a little bit homolog sitting here in this region. Here's the interaction. So it's a good lead start, but can be also used for, of course, for future drug discovery. Just showing a comparison, the SARS-CoV-2 has slight differences in this region compared to other PA-Pros or to other viruses. Here's just to symbolize the activity. We established an assay on this. And here are the compounds inhibiting the overall activity is 100%, reducing reasonable. So it doesn't mean these compounds are also in, we have here IC50 virus inhibition. I would say it's not perfect, but it's reasonable start. So these compounds you find in red wine, so I'm not recommending to drink red wine when you have a corona infection, but keep in mind also green tea is influencing this type of activity. Those are very interesting results, and we plan to keep on this line, looking at natural compounds in future more. And just to mention here, so our collaborator in Sao Paulo, here could perform the first mice and mouse experiments, hamster, sorry, with the MPRO inhibitor and with the PA-Pro, and we are seeing some very interesting effects. And only recently, we published this 4 weeks ago in Nature Comp Biology, and we dedicated this article to the honor of Professor Woman, and because the compounds coming from this institute and the fruitful collaboration with the institute, particularly with Professor Short-Hari. I would like to mention, you should establish this here. You can send crystals from any part of the world. All this you can do manually in the lab. Send to a synchrotron, and I understand there are some bottlenecks these days, but you may be able to solve this. And you can happily process and collect data from here. Again, the collaborators here, the Institute in Karachi Bioinformatics, groups on the DAISY campus. My group here, you see a group picture, and I was always happy. Here's Malik, Ashok Malik, Hina, and Najib. Both are assistant professors now at Mutter University, and I'd like to mention our late colleague, Wolfgang Völter. He brought me to this institute 15, 17 years ago, and he was named in Germany and friend of the world, and we are missing his advice. So, okay, and thank you for attention.
Thank you very much for that presentation. For this time for 1 or 2 questions. Open the floor. Maybe I start with a very trivial question. You alluded to one slide. Can you do your shooting your crystals through the laser beam or the beam source? How do you control the angle of the beam? Does that not affect?
No, we are shooting 10 to 10 or 10 to 5 crystals. We are shooting not one, we are bringing many.
But they must have different angles.
Yeah. And the software, latest software is checking it. And the processing software is telling you completely. There's one bar going up. So this is going fast, and the software is also so fast. You see in the minute range when the data set is complete. Or you take 100,000 images, then you are Things are so fast.
You don't have to align them. It's not like
It's over. I learned classical crystallography with space group orientation and all these things, and to be efficient, but these days, going so fast, you have to complete data set in seconds to minutes.
another question from the audience. That's on the back of there.
Thank you, sir, for your very informative session. Sir, there is some computational tool or some nowadays machine learning tools are available for screening compound. Is this result obtained from computational screening or machine learning screening is more efficient than this high throughput screening, or this may guide for best result, machine learning screening and computational virtual screening?
No, I understand your question, but this is a real experiment which is complementary to bioinformatics and others. And from my side, I would say we would not have predicted these compounds to be binding, for example, to the PH4, which is a complete new site. So no bioinformatics can predict this. On the other side, you need to consider solubility, which is always fine. So most of these compounds are not water soluble, so you need DMSO. Of course, you need to do biochemistry, biochemical assays. We did on top ITC, MST, binding assays, and bioinformatics. But the experiments you need, I would say, otherwise you're around to some extent.
Okay, so sorry, we're going to have to cut the conversation short, but I'm sure Professor Beck will be around to discuss things throughout the conference. So can we just join and thank you again for that